Okay, so let's get started, please. If any of you have ever been to my office, you'll see that on my door, there's this thing called, there's a bingo game, like five rooms. And it's like bingo, right? Where O is my last name, of course. And one of the squares is, okay, let's get started, please. Because I say that almost every time. And I say that basically every time. But the others are things like disparaging remarks about the teaching assistant, or gesticulations with hands to illustrate something, or mention of obscure mathematician. These sorts of things. Anyway.
Is the let's get started the free space?
That's right. It says basically a free space. Yeah. Okay, so today we're going to be talking about this density result called the Stone Weierstrass Theorem. So Stone Weierstrass Theorem. Right, and so what it says is the following: that if you have given any function that's continuous on a closed and bounded interval, then there exists a sequence of polynomials, P sub n, such that P sub n converges to F uniformly on AD. Okay. So what this is saying is that if we translate it into the language of the soup norm metric, this is saying that that polynomials are dense in the continuous functions with respect to the soup norm metric. Okay, and like I said last time, this is an important theorem, but I think what's more important for you as students is to see the technique involved. The proof will involve a technique called approximation of the identity, and that's something that is used in analysis quite a lot. So before we get started, I'm going to make some assumptions. So without loss of generality, we're going to assume that that our function is defined is 0 outside of the interval. Okay. So we have this function, and it's defined on AB, and we're going to define it as 0 everywhere else. Okay. We're also going to assume that its values at the endpoints are 0. Okay, so you've got this function on AB, and it goes something like this, right? You've got some continuous function, and we just extend it to the rest of the real line by making it 0 outside of the interval. Okay, and the third thing we're going to do is assume that AB is actually 0, 1. It doesn't make much of a difference. It doesn't make any difference. Okay. So those are going to be our assumptions. You'll see that if you can do it for such functions, you can do it for any functions. It's not difficult to see that. Okay. Okay. So Stone Weierstrass theorem, showing that continuous functions can be approximated with respect to the soup norm metric by polynomials. Okay. So here's the proof. This is pretty cool. So we're going to, let me put down sort of the idea first. So idea is we create what's called an approximation of the identity. Okay. We create this thing called the approximation of the identity, which will be a sequence of functions that we're going to call Q sub n. Okay. So Q sub n are going to be functions. These Q sub n are going to be functions on negative 1, 1. They're going to be real value functions on negative 1, 1. And we're going to construct them so that their integral is always 1. Okay, so the mass is always, mass of the integral, mass of the function is always 1. And that they'll have the following property, that given any delta in 0, 1, Q sub n will converge to 0 uniformly on the set where the absolute value of x is bigger than delta. Okay, so right, so you're going to have these guys Q sub n. Here's negative 1, 1. Here's 0. The mass is going to be 1, so you know how much area is under the curve is always going to be 1. But we also have this thing that whenever we fix a delta, so whenever we fix a delta here, here's negative delta, and we look at the sequence of functions on, so there's going to be some sort of sequence of functions, and they're basically the mass is going to start getting concentrated. Okay, basically, as n goes to infinity, the mass is going to become more and more concentrated towards 0. Okay, and so we want for any fixed delta, we have this requirement that on this set, right, the set where x, the absolute value of x is greater than delta, then the functions are going to converge to 0 uniformly. Okay, so basically they're losing, you know, well, this is the mass gets concentrated condition. Okay. Okay, and so, right, so, you know, whatever delta you choose, right, you could choose a very tiny delta, we know that eventually the mass is going to be concentrated on that little interval there. Okay, and it's going to be mass 1. Okay, as n goes to infinity, that mass becomes more and more concentrated towards 0. And you see that this is basically becoming something like the Dirac delta function. Right? The Dirac delta function is not really a function, right? Maybe you've heard about this thing. You know, it's this thing that is 0 everywhere, but has an integral of 1. So like it's 0 everywhere except at the origin, and it has an integral of 1. Okay. That's not possible, right? You can't have a function that has only values at one point and has an integral of 1. Okay, that's actually what's called a distribution. Okay, which you will not see, which I think the Russians call generalized functions. Okay, so the Dirac delta function is this thing called a distribution. And you see that these functions, in some sense, are getting closer and closer to that Dirac delta function, right? Each one of them, right? Somehow, in the limit, they're turning into the Dirac delta function. The limit of these guys is the Dirac delta function. Okay. Why is this called the approximation of the identity? It's because we're going to be doing a certain operation called convolution. Okay, so we're going to do something called convolution. We'll be convolving these approximations with the function. Okay, and it turns out that the identity element, you want to think of this as a sort of multiplication of functions. It's really an averaging of functions, but you want to think of it as sort of like a multiplication. And it turns out that the thing that acts as an identity, that acts as 1, is the Dirac delta function. When you convolve with the Dirac delta function, you get back your function. Okay, So these things are not the Dirac delta function, but there's some sort of approximation of it. And you think that as Qn tends towards infinity, you're somehow you're going to recover your function back. Okay, so that's an explanation of the terminology here. Okay. Okay. Right. So okay. So how are we going to construct the Qn? Here's a construction. So we're going to let Qn be 1 minus x squared to the nth power, as n is 1, 2, 3, etc. Okay, and this is just on -1, 1. Okay, so right, so it's 1 minus x squared, right? So 0, you have something like this, right? It's a parabola going downwards, right? The first one is this parabola going downwards, and then as you take powers of it, you see that this 1 gets preserved, right? The 1 gets preserved, and everything else gets shrunken. So you have things like this, and things like this, right? Right? As n gets bigger, you get these things. You get these sorts of things, right? And so that's basically the idea. Okay. Now we do have to guarantee we do want to make the integral 1, so we need to fix it up a little bit. So we let so this is not actually the right answer. We're going to say that it's equal to some constant times that. Okay. Where, as you might guess, Cn is chosen. Cn is just the integral of 1 minus x squared to the n. It's a reciprocal of that, right? It's chosen so that the integral of this thing is 1, right? Okay, so those are our approximations of identities. Okay, so it has the first property, so obviously property 1 is satisfied. Okay, now as for property 2, as for property 2, there's sort of two calculations involved. The first is to see that if you actually calculate that integral, then it's smaller than the square root of n. Okay, so I just leave that as an exercise. That's a calculus exercise. You just need to integrate that thing. Okay. And then the second part of it is to notice that if we are on this set, well, sort of obviously, x is absolute value of x is bigger than absolute value of x squared is bigger than delta squared, right? So 1 minus absolute value of x squared is less than 1 minus delta squared, right? 1 minus the bigger thing is smaller than 1 minus the smaller thing, right? Delta is bigger than 0, right? Okay. So what does that tell us? That tells us that right. So remember what our Qn is, right? Right. So Qn, right? Qn is c sub n 1 minus x squared. So that's smaller than the square root of n times 1 minus x squared to the n. So this is smaller than the square root of n times 1 minus delta squared to the n. Okay, and then this thing goes to 0 as n goes to infinity. Right. So that gives you your uniform convergence. You can, if you want, you can see this by L'Hopital's rule or something like that. If it's not clear. Right. You've got this thing that's smaller than 1, and you raising it to the nth power. Right. That's taking this is like square root of n over something to the nth power, over a constant to the nth power. Right. So over a constant greater than 1 to the nth power. Right, so that clearly goes to 0. Okay. Okay, so in any case, this is the construction of the approximation of the identity. Okay, so what are we going to do with it? What do we do with this thing? We let p sub n be the integral from -1 to 1 of f of x plus t q n t dt. Okay. Okay. Is that okay? Okay. So this is basically what one calls a convolution. So the convolution of p sub n with x. Okay. And this is a super important idea that you'll see in higher analysis courses if you take them. Okay. So our claim is that these are the Pn that we're looking for. Right. We wanted to construct a bunch of polynomials that converge uniformly to f, and this is them. Okay. So there's two parts to this claim. Right? The first is that these p sub n actually are polynomials, and the second claim is that the p sub n actually converge to f uniformly. Okay. And again, in your mind, you sort of keep this vague notion that these are an approximation of the identity, and so as n goes to infinity, we get something like the Dirac delta function, and the Dirac delta function would when convolved with f, would just return f exactly. Okay. So that's the intuition of what's going on here. Okay. So let's prove claim 1. That these things actually are polynomials. Okay. So, sorry, I forgot to say this should be Pn of x. So the polynomial at point x is defined to be the integral of f at x plus t against q and t dt. Okay. Okay. So let's see why that's true. It's pretty straightforward. let's look at it. This thing here, f of x plus t, qnt dt, equals, so what's the point here? That as t ranges from -1 to 1, right? We've got this t plus x, right? So t only needs to go up to 1 minus x, right? Because f is 0 past 1, right? Remember, f was this thing between 0 and 1, and it was 0 here and onwards, right? We had some function f like this, right? So t only needs to go up to 1 minus x, because past that point it's 0. Okay. And similarly, t goes down to negative x. Okay. Okay. So we get f of x plus t qnt dt. And then we do a change of variables on it. Let s be x plus t, right? And so this becomes the integral from 0 to 1 of f of s q sub n s minus x ds, which, if we write it out, is f of s times, remember what q sub n was. Q sub n was 1 minus the argument squared to the nth power. Okay, but you see what we're going to get here. There's going to be basically, this is going to be a polynomial in x, right? Because all you're going to get, you're going to have some powers of x in there, right? You just have some powers of x, and you're going to there'll be some constants on it because you integrate over s. But that's just going to give you some constants multiplying the powers of x. Okay, so this is going to be a polynomial in x. Okay, right? Like if I had something like the integral from 0 to 1, s squared, and then some power of x here. You see that I pull the x out and I just get some constant times x. That's all that's going to happen here. We're going to get powers of x multiplied by some constants. So it's going to be a polynomial. Okay, any questions? Okay, so now we get to the cool part. I know. I think it's cool. So it is cool. Okay, now we get to the cool part. Okay, so we want to see that this thing converges to F uniform. It's not that cool, but it's pretty cool. Okay. Yeah. Okay. Okay, so we want to see that these guys converge to F uniformly. So proof of 2, right? That the Pn converge to F uniformly on 0, 1. Okay. So what does that mean? Of course, that means that we want to show that given any epsilon, there exists an n such that when you're past that n, then the size of Pnx minus f of x is smaller than epsilon all over the set. right? All of it at interval 0, 1. Right? Okay. Remember again, f is only defined on 0, 1. Okay. So let's look at it. Let me do some erasing first. So you say, well, let's look at it. Pn of x minus f of x. What is that? Well, that's just the convolution of Qn. So that's the integral from -1 to 1 of f of x plus t Qn t dt minus f of x. Right? Just by definition, that's what that is. Right? Now we play a funny trick, which is we sneak in a 1. This is going to be the weirdest looking 1 that we've had all term. Okay? I know we've had some weird looking 1s, but this is going to be even better than that. So here it is. 1. Right? This was 1. So we slide back, we multiply this f of x times 1. Okay. So we get the integral from -1 to 1 of f of x plus t minus f of x times qnt. After we combine those two integrals together. Okay, everybody all right? Right. So we multiply this guy by this 1 here. Right? We brought the f of x inside, and then we combine the integrals together. Okay, so nothing fancy, except using the approximation ray identity. Okay, so now let's see, what are we going to do? Let's see. So we have that we're gonna break this into 2 parts. We're gonna break this integral into 2 parts and then control each part separately. The breaking will depend on. We're gonna break this into the part where the q sub n are small. Remember, we said that the q sub n can be made arbitrarily small outside of some neighborhood of the origin, right? That was part of the construction, right? That outside of some delta neighborhood of the origin, the q sub n converge to 0 absolutely, uniformly, right? So let's do that. We're going to break it. Say, okay, this is less than or equal to the integral on that interval, right? Plus the integral outside of that interval. The integral outside of that interval. Okay, and we use the triangle inequality, right? So we break it into 2 parts. We break it into 2 parts, and then we move the absolute value inside using the triangle inequality. Okay, you can probably tell me what to do at this point. We're trying to make this thing smaller than epsilon, right? We're trying to make these things smaller than epsilon. Of course, we're going to make each of them smaller than epsilon over 2, right? How can we make this thing smaller than epsilon over 2? Remember what f is. F is a continuous function on 0, 1. Okay. talk to your neighbor for 1 minute and see if you can control one or the other or both of these terms. So the way you want to think is like, well, look, I can basically make this 0, right? If I can make this 0, then this thing basically becomes 0, right? So clearly we can do something good about this. So what do we do exactly? How do we do this rigorously? Anybody want to say something about how to control either part? No? Nobody dares? Mo?
I'm not sure.
No? Okay. Okay, so, well, think. Lynn?
Just the thing where it's 0 outside of a certain range of values.
Yeah, so we can, this thing is converging. We're away from the origin. We're away from the origin, which means that we can make this thing as small as we want, right? We can make this thing as close to 0 as we want, right? So we know that since Q sub n converges to 0 uniformly on this outside away from the origin, we know that there exists an n such that if we're past that n, then Q sub n of t is smaller than whatever we feel like. Let's say epsilon over 2 for now. Okay. Actually, we need something a little bit better than epsilon over 2 because we need to control this thing too, right? But this thing is easy to control because our function is a continuous function on a compact set, right? So what do we know about such functions? Continuous function on closed and bounded interval is bounded, right? The extreme value theorem tells you that it's bounded. So we know that there's some bound, let's call it m. And then we do something very crude. We say, well, look, this difference is controlled by the sum of the absolute values, right? This thing is controlled by this plus this, right? Which is smaller than 2n. Right, it's crude, but we don't care. Okay, so this thing is smaller than 2n. We make this thing smaller than epsilon over 2 times 2n. Right, and so we get that this thing on the right is going to be smaller than this thing on the right is smaller than the integral of 2m times epsilon over 2 times 2n, right? Integrating over the over 0, 1, say. So we're just going to go over the whole interval 0, 1. I'm sorry, negative 1, 1. Negative 1, 1. In that case, I need another 2. Okay. So I get epsilon over 2. Right? I need another 2 because I get a 2 when I integrate from negative 1 to 1. Okay, so that thing on the right is controlled by epsilon over 2. How about the thing on the left? How are we going to control that? Well, we don't have anything good. We don't have some sort of numerical bound on the Q subents, right? They're going to become arbitrarily large in value, right? But we do have this f of x plus t minus f of x, where t is small, right? T is small. We can make t as small as we want, right? Our delta was up to us. We broke this thing up into two pieces, right? So that delta is our choice, okay? So if we make our if we make our delta really tiny, well then, what kind of control do we need here? F of x plus t minus f of x, where t is tiny. T is tiny, and x is any point in 0, 1. What do we need about f to get control of such a thing? Keshav? Continuity, not just continuity, but uniform continuity, because x could be anything in 0, 1, right? So as x, x can be anything in 0, 1, but our change is, the difference between the 2 points is less than delta, right? So as long as we have control over the whole over the difference of values, given that the values are within delta of each other, which is uniform continuity, then we're good. And we do have uniform continuity because we're a continuous function on a compact set. Okay, so that does it for us. So f is uniformly continuous, right, on 0, 1. So we know that there exists a delta such that, right, if the distance between 2 points, A and B, is smaller than delta, then the distance between f of A and f of B is smaller than epsilon over 2. Okay? So use that delta, right? Use that delta. So this should be kind of in between here. Use that delta, and we break the thing up into 2 parts. Right? We break the integral into 2 parts, and we see that we get here that this thing is controlled by epsilon over 2 times qmt dt. Again, we'll take the integral over the whole space, negative 1, 1, but that gives us epsilon over 2. Right? And so we get epsilon, the epsilon that we wanted. Right? So we can make this thing smaller than epsilon since this stuff here. Okay. So that is the proof of the Stone Weierstrass Theorem. I hope you like it. It's kind of cool. And you see what the point of the approximation of the identity was, right? We wanted this thing whose integral was 1, so that we could play this trick here, right? So we could slide it in and then use the continuity of the function, right? Use the uniform continuity of the function to get control of this part, right? And then the second property of the approximation of the identity allows you to split it into 2 parts, one of which is controlled using the continuity of the function, the other of which is controlled using the uniform convergence to 0 of the approximation. Keshav?
Is the Q identity we're using what's special, or can we use something else?
You can use a lot of other things, yeah. Yeah, so like I said, in some books, these things are just called good kernels, right? So there's a whole bunch of good kernels. It just has to have, what did we need? Think about what we needed. It had to be an approximation of the identity, right? The integral had to be 1. It had to have this uniform convergence outside of the neighborhood of the identity, right? Uniform converge to 0. But there was that last thing we needed in order to make it a polynomial. Okay? If we didn't care about it being a polynomial, we could have used just those two qualities would have been fine, right? And we would have gotten things that converged uniformly to our function. They wouldn't have been polynomials, though. So what's special about our choice of Q sub n is that we designed it so that we would get polynomials when we convolve with it. Yeah, but often you don't care about that. One doesn't care about that. All you care about is that you can approximate your function. Okay, any questions? Okay, so let's see. Okay, so I thought I made some choices of things to look at from chapter 8 that I hope you'll like. They're basically the applications of stuff that we've seen in chapter 7, and they are related to, I've been talking about like complex analysis every once in a while. They're related to certain results in complex analysis. Okay. So yeah, this is sort of sets you up for a course in complex analysis. Okay. Okay. So applications to power series, or really what we want to say are analytic functions. Okay, so let's start off with the definition. So this is chapter 8. So here's the first definition. Any function f that has a power series expansion in other words, can be expressed in the form f of x equals summation c sub n x to the n from n equals 0 to infinity, is called an analytic function. So it's a function that has a power series expansion. Okay. And this might be, this could be x minus a to the n, so we're just going to be dealing with real functions on the real line. Okay, so this is for some point a in the real line. Okay, so you've seen these sorts of things before in calculus 2, right? Taylor, I think one of them is called Taylor series, the other is called Maclaurin series, or something like that, right? But anyway, they're just power series centered at 0 or centered at some other point. Okay, and any function that's expressible like this is called an analytic function. And in the book, we're just gonna, for simplicity, we're only gonna deal with these guys, the guys who are centered at 0. The theory, of course, easily translates to the series that are centered at some other point. Okay, so remark, we'll only consider the cases when a equals 0. Okay, so let's recall something, that any such power series has a radius of convergence R. Okay. Do you guys remember how we got that radius of convergence? Just to remind you. How did we get the radius of convergence? It's okay. It's okay. We use the root test. Okay, right? So recall that we obtained it via the root test. Right. Remember what you do. You take the lim sup of the nth root of the absolute value of the nth term, right? As n goes to infinity. Right? And as long as that thing is less than 1, then you have convergence. Right? As long as this thing is less than 1, then Cn xn converges absolutely. Kind of obviously absolutely, because when we do the root test, we take the absolute values. Okay, so you remember what that turns out, right? You need that, i.e., you need that this thing times this needs to be less than 1. In other words, x needs to be less than 1 over the nth root of the absolute value of the nth coefficient. Right? So this thing here is your radius of convergence. Right. This thing here is your radius of convergence. Okay. Okay. Now we're going to show something pretty cool, which is that if you're an analytic function, you are infinitely differentiable. Okay, so every analytic function is automatically infinitely differentiable. Okay. Now the cool thing in complex analysis is that being differentiable forces you, being what's called complex differentiable, forces you to be an analytic function. So in complex analysis, if you're once differentiable, then you're infinitely differentiable. Okay, that's very, very much not true for real, in the real, when you're doing real analysis, right? But for complex analysis, the quality of being differentiable is very binding. It's very constrictive. So it forces you to satisfy a set of differential equations called the Cauchy-Riemann equations. And that sort of constrains you to be a very, very good function. So differentiability puts all your functions in this tight straitjacket, and then they all have to behave very well. Okay, and that's not the case for real differentiation. So that's why everything works out kind of nicely in complex analysis. Okay, so here's the theorem. Suppose your function has a power series expansion, and it converges in some interval negative RR. Okay, so that's its radius of convergence. Then the series converges uniformly in any negative r plus epsilon, r minus epsilon, closed interval. Okay, so you have your radius of convergence, negative RR, and what this is saying is that if you take any closed interval that's contained inside there, then you've got uniform convergence on that closed interval. Part 2, f is continuous and differentiable in R, negative R. And further, its derivative has a power series expansion. And the power series expansion is obtained by differentiating that guy term by term. Okay. So, it kind of works out as you hope it would, right? The derivative of this thing, the sort of infinite polynomial, looks like the derivative of the infinite polynomial that you would expect. Okay. That requires proof, and so that's what we're going to do right now. Okay. Okay, so we're just going to prove these two things. And you see that this second fact implies the infinite differentiability, right? Because this says if you have a power series expansion, then your derivative exists and looks like this. You can do term by term differentiation. So people call this like term by term differentiation. Right. Term by term differentiation is possible, right? You don't have to worry. You can pass the derivative through the sum. Right? You can pass the derivative through the sum and get the sum of the derivatives of these things. Okay. So, right, but then you would know that your derivative in turn has a power series expansion, right? And so it is continuous and differentiable, and its derivative will be obtained via term by term differentiation, and so on and so forth. Okay. So any analytic function is infinitely differentiable. Okay, so that's what this theorem gives you. Okay, so let's get it. It's not hard using the tools that we've created over the last couple of weeks in chapter 7. So first part, we want to see that this thing converges uniformly in any negative r plus epsilon r minus epsilon. Okay. So, kind of does anybody want to make a guess as to what tool we're going to use to show uniform convergence of this series? We basically have only one tool to show uniform convergence of a series, which is anybody know? It's okay. I understand it's risky to say anything. The Weierstrass M-test. Weierstrass M-test. That is our tool to show uniform convergence of a series. Right? We want to see that. Remember what it says. If we can get bounds for each of these summands, and the sum of those bounds converges, then this thing converges uniformly. Okay. So that's what we're going to use. Part 1. Weierstrass M-test. Use Weierstrass M-test. Okay. So we see if x lies in negative r plus epsilon, r minus epsilon, then of course the absolute value of x is smaller than r minus epsilon. Okay. But then, we get that Cn x to the n is of course smaller than C sub n r minus epsilon to the n. Right? If I take the opposite opposites. Okay. So we get these are our n sub n's. Right? These are the m's that we want for the Weierstrass M test. Okay? Okay. This thing converges. C sub n r minus epsilon to the n from n equals 0 to infinity converges. Why? Because this thing converges on negative RR. Right? This thing converges on negative RR, so it certainly converges at r minus epsilon. Right? R minus epsilon is sitting inside here. Right? Of course, epsilon is chosen, so that epsilon is smaller than r. I don't have to say that. Okay. Okay, so we're done. That's it, right? Right? This thing converges, so by Weierstrass M test, the summation, the sum of these guys converges uniformly. Okay. That's right. So our sum of the mn's converges. So summation Cn xn converges uniformly. Okay. Part 2. It's actually not hard. So you think, consider this thing. Summation n c sub n x to the n minus 1 from n equals 1 to infinity. Okay. This series that we're hoping will correspond to our derivative. Okay. If we think about its radius of convergence, right, we're going to take the limit of the nth root of the absolute value of n c sub n x to the n minus 1 as n the lim sup of that, right? But you see that that's going to be the same thing as the lim sup of c sub n x to the n, right? Because you're taking this x to the n minus 1 over n, and n goes to infinity. Right? So this basically turns into, right? This turns into just the absolute value of x. Right? N to the 1 over nth power also goes to 1. Right? And so we end up with the same condition. Right? We need this to be smaller than 1, and our radius of convergence is the same. Its radius of convergence is just going to be 1 over this, the limit of these guys. Okay. So it has the same radius of convergence. Since this is true. Okay. So what do we know? We know that this thing converges uniformly, right? So this derived series also converges uniformly on negative r plus epsilon, r minus epsilon. Okay. Now, remember, we had this, right, and what that means, of course, is that the sequence of partial sums converges uniformly, right? The sequence of partial sums, we call them sigma sub capital N, summation up through N, right? N from 1 to capital N. This thing converges uniformly. Okay. So remember the theorem that we had about convergence about when we can alternate, when we can commute the differentiation and the limit. Do you remember that? It wasn't so straightforward. It was kind of funny. We had to have a sequence of functions that converged at a single point, and their derivatives had to converge uniformly. Right? The derivatives had to converge uniformly. It wasn't just that uniform convergence allows you to commute these things. It was you had to have the derivatives themselves converging uniformly. Fortunately, that's what we have. Right? We've got our sequence of functions. Right? Our sequence of functions will be the partial sum sequence of these guys for this series, and right? It converges actually on the whole interval, so it definitely converges at a point, right? And we have that the derivatives of them converge uniformly, so we can change the order. Okay. So by our previous theorem, by an earlier theorem, we can change the order, right? That the derivative of the limit. The derivative of the limit equals the limit of the derivatives. Okay, but that's exactly what we want. This thing here is our function, right? This is f, right? So f prime of x equals the limit of the derivatives. The limit of the derivatives is this derived series here, right? So we get exactly this. That's this, what I just wrote over there is this box statement. Right? The derivative of the limit, which is the function, right? The derivative of the function equals the limit of the partial sum sequence of this series here. In other words, it's this series. Okay, so that's cool. I hope that's kind of interesting to you. That whenever you have an analytic function, it's infinitely differentiable, and then you can get the derivatives by doing term by term differentiation.